No, there will be nothing playful. Well, good morning, everyone. So you may have expected Daniel here, but there's been a last minute switch in program. So sorry to disappoint you with that. I need to click. All right. Yeah. So in this talk, I'll talk about games and loop integrals. But you can sort of decide about which section you want to hear more. So I'm a physicist, and I try to compute loop integrals, specifically 4 and 5 loops. So it's a rather tricky business. But in general, in this field, there are two really nasty problems. So the first of all is numerical integration. So at some point, when you reach even 2 loops, the expressions become so large, it takes an extreme amount of time to numerically integrate. A second problem is that, well, even at 2 loops, if you try to compute the integrals themselves analytically, you also run into lots of problems. And there are some methods, but they take months and months to find solutions to the integrals. So we had the idea to apply methods from AI, specifically those used in games, to problems in high energy physics, and see how far we can come with that. So the first problem I'll focus on is simplification of expressions. Right? So a lot of people here have worked on Monte Carlo integration and improving the algorithms themselves. We try to improve the input of the algorithm. So this is an example of a very short expression that one may want to numerically integrate. So basically it means you start sampling. So for all these variables, you just fill in some numbers. But of course, there are lots of operations going on here, so it takes time. So it would be nice if we can shorten this expression so that we reduce the number of operations so that we can speed up Monte Carlo integration. Now, this is a short expression, so expressions we normally get have millions of terms and, well, more than that in operations. So you can't really do any fancy stuff like factorize it. So if you can say, please factorize it for me, it will just not give you any result anytime soon. So we're going to go back to basics. So one basic thing you can do is to pull variables outside of brackets. It's called Horner schemes, which you've probably learned in high school at some point. So let's say you have that polynomial, and you decide to, well, so it has 9 operations, 9 multiplications and 2 additions. If you decide to pull the x out, you'll reduce the number of multiplications to 4. But you could have also decided to do to extract the y first, and then you're left with 7 operations. So the order in which you can extract variables influences the result. So now the question is, can you find an optimal or near optimal ordering so that you reduce the number of operations the most? Well, sadly, this problem is NP hard, and we're going to make the problem a little bit more difficult, because after you extract things, extract the variables, you can also remove common sub-expressions. So here is like a 3 representation of an expression, and you can see that the b times a plus e occurs in both. So you could extract that one. So what we want to do is find a Horner scheme, build the Horner scheme, extract the common sub-expressions, and then try to do that in a way so that the number of operations is minimized. So this is a bit tricky, because it could be that a good Horner scheme actually produces less common sub-expressions than an average Horner scheme. There are also no heuristics available, sadly. And this part is actually the most important problem we have, is that evaluating a scheme, so building it, extracting the variables, finding all the common sub-expressions, is really slow. So it could take 1 second for an expression, and one of our benchmark expressions actually took 25 seconds. So you have to wait 25 seconds to even construct the thing. So it means you have to be a bit careful with just randomly sampling, randomly trying to find a good scheme. All right, So we were inspired by the successes in Go to try Monte Carlo tree search. Has anyone here used Monte Carlo tree search? Raise hands. Okay, good. Has anyone heard about multi-armed bandit problems? One person, nice. Okay, sweet. So then I'll just explain what Monte Carlo tree search is, because it could also be very useful in other fields. So first of all, it has been successful in Go since 2006. It's been used in Go engines. It's also used rather recently in AlphaGo, you know, the Go program that beat top-tier human players. So how does it work? Well, normally, let's say if you want to solve chess, in chess you just try every move of like 5, 6 levels deep, and then you find the best moves you could have done. Because you sort of have a feeling after, if you look at a chessboard, how well you're performing. In Go, that's more tricky. So in Go, if I give you a random board position, it's really hard to see who's winning, which makes and the number of options in Go is also enormous. If you've got a 19 by 19 board, you can't really go 6 levels deep. So the idea is to start exploring moves, but in such a way that the moves that you think are most valuable, you'll try that first. So it's a best search way of building a state tree. Now, in our problem, so in Go, the state tree would be that you put the stones on the board and you've got new positions. In our problem, each node will be a variable which you select in the scheme. So if you want to select X first, that will be the top level node. If you select Y after, then you'll that will be the child node of the X. Okay, so the most important thing in Monte Carlo tree search is deciding where you want to expand the tree. So here I already have a partial tree where you've tried the X first and then the Z, and you've already tried the W even. But now the algorithm decides that here at the Z you want to try another variable you want to put in the scheme. So in Go, this would mean another position you want to explore that you haven't tried before. So how do you decide where you want to expand the tree? Well, there is a criterion for it. It's written down like this. But let's ignore the formula for now, and let's go to the multi-armed bandit problems. So imagine you have you're in a casino, and you have 6 slot machines, and you want to find the slot machine that gives you the best odds. So how would you proceed? It's a stochastical problem, so you have to try, and it could be that you're just unlucky, right? So you just start trying all of them, and you see, you keep track of how often you win. And the one where you win the most, you try more often, of course, because that seems to be the more rewarding. But it could be that you have actually been unlucky with the other slot machines, because it's stochastic. So sometimes you have to try those as well. So you have a sort of problem where you can decide if you want to explore, so try the other slot machines you haven't tried in a while, or to exploit, where you just go for the slot machine that gives you the best odds. Now this problem has actually been solved. So there is like a ratio of how often you should explore or exploit, and that formula looks like this. So you pick the child. So if you're here, you pick the child that has the best win ratio. So X is the score of this node, and N is the number of times you visited it. And the second term is a ratio of how often you visited that child node compared to the parent. So in the slot machine language, it would be how often you haven't really explored it a lot in a while. So this ratio is controlled by the CP thing. So CP is a constant you have to tune that decides if you want to explore more or exploit more. And in Monte Carlo tree search, you apply this formula at every level. So you always start at the top, and you ask, which of my nodes would I like to explore more? And so here in this example, you've chosen the X to explore and then the Z. And at the Z, you stop. Because here, you haven't explored every child node. So here you say, OK, let's try another option after the Z. We've tried the W, but let's say we want to try the Y now. So that's the next step in the algorithm, is expansion. And in this case, it's random. So you randomly select a node. In the Go language, it would be that you just pick a stone and put it in a random position. Now, in chess, you'd think, OK, well, great. Now I'll just evaluate this position. I'll look at the board, and I see how good does it look. But in Go, you don't have the evaluation function, and we also don't have it. So the only way to sort of know how good this partial scheme is so far, the X, Z, Y, is to sample it until the end. So you just fill in the scheme randomly after this, and you see how good is it. So in Go, you would decide, you would play it through the end, and you see, did I win or not? Now, of course, this is stochastic. So you have to do this a lot of times. So in Monte Carlo research, you just start from the top again, and you start repeating this process. And so as you go along, the tree will grow, and you'll have more plausible statistics, especially for the first option. So in games, that's very important, right? You do this to select the next stone you want to put on the board. So that's at this level. So you've got good statistics there. So in the end, if you've obtained, if you've won or not, or in our case, it's like the ratio of compression, you'll backwards propagate that value through the path you've taken. So you will update the score of every node you've come across. And you've also increased the number of visits. And in all, that would mean that this number X here changes for the nodes, and you just try, and you just keep on doing this until you find a nice solution. So this is how it works. This is also how it works in AlphaGo, sort of. So they're sort of cheating for many reasons. I'll name some cheats. So the first is their random scheme isn't random. They've used expert knowledge there, where if they encounter certain patterns, they know what the experts would do, so they program a solution in there. So that's not really random, so that sort of goes against the spirit of MCTS. The second thing, which is actually even more questionable, they set the CP to 0. And third, in AlphaGo, they also use an evaluation function, which they've trained using a neural network. So they sort of mix it up. So they use the stochastical Monte Carlo results and their pre-trained evaluation function, which they obtain through different means. All right. So great. So using this method, we can simplify expressions by, well, it depends a bit on the factor 10, 20 compared to the original, if you wouldn't do anything, which really helps because the expressions become smaller, and it's all compiled into a binary anyway, and the binary also becomes smaller, so the compiler can do more optimizations. So all in all, it's a good improvement. But one problem we have is that tuning this parameter is very difficult, and because it takes samples to tune. And as I said, sampling is very expensive. If you take 1 second for each sample, so if you just do, normally it requires 1,000 samples to just get something decent, you're wasting a lot of time. So what we tried is that we thought, okay, let's investigate like this, what the state space looks like of our problem. So for this, we define a neighbor in a Horner scheme. So here you have the Horner scheme ABCD. So you first extract A, then B, then C, then D. And the neighbor is just a swap in that list. And if we do this, we get sort of a result like this. So the number of operations is here, and the frequency that a search that just swaps and only goes to better ones. So it's like a stochastic hill climbing. that's the frequency of how often you end up with a certain number of operations. So obviously here is the best, is what you want to achieve. So if you do 1,000 steps, so 1,000 swaps, you'll have this spectrum. If at 10,000 you get this, and 100,000 this. Now if you would just look at this, you'd think, oh wait, this is a local minimum there, because we get stuck, because we only go to a new position if a swap yields a reduction in the number of operations. So this would imply that you'd need some sort of simulated annealing to also get out of gaps. But actually, if we increase the number of samples, we see that we only end up here. So that's interesting. So this means that in this multi-dimensional problem, these things are actually not local minima, but are saddle points. So there is a way around them to escape. It only takes time. But this is interesting. So they're not really local minima. And second of all, if you start swapping, we also saw like how many of the neighbors have the same number of operations. And actually it turns out that most of them do. So you're sort of stepping, moving to the side, and you're not really changing. The environment isn't really changing. So our state space looks sort of like a rice field, where nothing happens, and at some point you sort of drop. And so this actually means that we can also use a simpler algorithm, than MCTS, without tuning, because we know that we don't have to take into account local minima that much, because we don't really see them. And we can use the time that you normally spend on the tuning to just simplify the expressions. Great. So I also wanted to show you some quick stuff we did with higher level loop, but I won't go into details too much. I'll just show how difficult some of the problems are that we have. So this integral here is a 5-loop integral in QCD. Those are the ones we want to compute. If you just write out the Feynman rules, that's what you normally do if you want to compute an integral, then this will give you 12 million scalar integrals. That's a lot. And they're all 5-loop, and it's all rather terrible. And if you start trying to reduce this using certain methods, then you'll also end up with more than a terabyte of disk space in expressions. So it's really nasty. But I just quickly want to show you how we solve those things anyway. So we use integration by parts identities, which you may have heard at some point, you may have tried. So basically it works that you find rules that can knock out one of the lines in the integrals. So for example, if you've got this 3-loop integral, you can knock out the top line. But it's also possible to knock out one of those lines at the side using a rule that you can construct. Now if you keep on doing this, you can build this very nice graph where every node is a topology, and every line line here is a line that you can knock out. So we completely automatically generated this program that can reduce any 3-loop diagram all the way down to nothing. So if you've got this, you've basically solved the problem. Good, but 3 loops is 3 loops, right? That's already been done. So this is the 4-loop one. It's a bit more nasty. So if we zoom in, we see that there's a lot of connections, of course, and a lot of those red things. And here in this graph, the red topologies are topologies for which we don't really have a solution for, at least not one that you can get very easily. So for those, we have to solve systems ourselves. So I'll very briefly sketch what we do. So let's say we have this integral here, and where each of the edges have an index n. If the index becomes 0, the line is gone. So it's sort of the power of that line. And from IPPs, you can get equations like this. So for example, these two. Now, this equation lowers from a lowest index 1, but increases index 2. So if you keep on applying this, then for one of the branches, the n1 will become 0. So that's good. So you've reduced the topology. But for the others, it just explodes. The NP goes to infinity. But if you can find another equation with an n2 plus 1, then you can combine them in such a way that you knock out the bad terms, and you find a rule that will always increase one of the indices down to 0. Now, at the moment, we use computer-assisted methods to find solutions. But we are currently investigating if we can use some AI here too. Or maybe like SMT, so satisfiability modular theory methods to automatically solve our systems. I'll just show you what one of our solutions looks like. This is a manual solution we found for a topology. So it's several pages long. And this is only a rule to reduce one of the indices to 0. So it's really nasty. Anyway, so finally, we've also have some physics results. So we computed the 5-loop beta function for a general color group early this year. It only took 6 days, so that's good. We've also recomputed Higgs to BB bar with 5 loops and the R ratio. That just took a few hours. And quite recently, we've computed the Higgs decay to gluons at 5 loops. This is a very nasty calculation. It took 2 months. But yeah, so that's it. Any questions?
Thank you very much. So we have time for questions.
Okay, that was a very nice talk. Thank you.
So you have to speak up.
All right, so did you have a chance to compare, or are you in a position to compare your expression optimization algorithm with existing ones that are available on the market?
So yeah, at some point we have. But for the expressions we tried, most of the existing software just never finishes or crashes because it runs out of memory. So yeah, so indeed we haven't tried all of them, but Mathematica one, that's a disaster. That's not going to get you anywhere. We also compare it to a rather simple heuristic you can try. That was used in, I think, 2 software packages. So in one of our papers, we have a comparison for this, yeah. Well, I should mention that those expression simplification things are all implemented in Form. So in Form 4.1 and 4.2. So you can also try it at home.
More questions? So the compilers also have this sort of algorithms implemented to try to reduce the complexity at compile time.
Yeah, so what the compilers do, I guess, is recycling of variables. So when it compiles the code to do the computations, yeah. But at some point, the compiler will also give up if you've got a 4 gigabyte binary. Then it's just too expensive to do all those optimizations.
Do you know what technique compilers use?
Well, so it's different. So they look at, so if you compute a part of it, they can recycle variables, and we can recycle how do you call it, the registers, for example. So it's a bit tricky and very different from what we do.
Any more questions?
ISO languages disallow reassociation of parentheses, so it's actually illegal for a compiler to do a lot of what they're doing, although optimizing compilers will do it anyways because they know people want it. But so there's a tension there. I work for Intel, and I deal with Fortran users who complain about those issues. So there's a fine line between optimization and correctness in floating point reassociation. But DSLs can obviously do whatever they want, and that's a good thing.